director is there. Tiwari Saab, you are there?
Yeah, I have joined. Namaskar, sir.
I can't see that. Oh, hello, Viren.
Namaskar, sir.
Can you hear me? Namaste. So you go ahead, you tell me what to do.
Thank you, sir. We will start just to brief about this program to all the participants, and then we will have your kind of blessing words before we start the 2 weeks long program online. And finally, after this, the initial phase, we will conclude, and then we will start your presentation, our inaugural lecture. So let me start this with greetings and all best wishes to all of you in this challenging time. And we have fortune of having one of the very distinguished earth scientists in the country, in fact in the world, who is also very to impart the knowledge to the young generations. And we wish to first thank him, Professor God, for agreeing in a very short notice. In fact, only a few days before we have requested him to deliver the inaugural address and inaugural talk, and he kindly consented for the same. The most important part of this entire skill development program is enabling the young people to do what they were not able to do while they are working at the remote places, at the places where there are not enough facilities or the techniques known to the faculties or the people. So this program is also planned to see that how best we will be able to engage ourselves with the young generation in order to skill them and empower them towards doing good science, and also utilizing the science part for the progress as well as the benefit of society. I will not take a long time between you and the speaker today, but I wish all of you very safe and fruitful year ahead, as well as a very successful this skill development program. It's over to you, Dr. Bansal. Abhay? Is Abhay online?
Yes, sir. Yes, sir. Good morning, sir.
So Dr. Abhay Bansal is coordinating the skill development program from CSIR. So thank you very much, Abhay. Could you please brief all our participants and the attendees regarding this program?
Good morning. Good morning, Professor Vika God, Chief Guest of the Day. Dr. V.M. Tiwari, the Director, NGRI. Professor Dr. Purnachandra Rao, faculty member and students. Good morning and warm welcome to all of you. So let me share my slides. I'm facing some problems, sir. Just a minute. Just a second, sir. Just a second, sir. I'm doing.
Abhay, you can speak while it's loading.
Yes, sir. The skill initiative program started in 2016, all our CSIR labs, and where the then Minister of Science and Technology and Vice President of CSIR inaugurated across all the labs. So CSIR in the pan-India presence and almost 8,000 scientists and technical staffs. The CSIR lab is well equipped with instruments and faculty and the latest research to aim to train our younger generation about the various technique and instruments, where, as our director also said, the universities, the students face problem in the practical aspects to aim to enhance our knowledge of our students about the practical aspects of the various methods. So CSIR NGRI also started 5 training program every year, and we trained many participants all over the country. And in this training program, 61 participants are attending from various parts of the country. Is visible? My slide is visible?
No,
My slide is visible?
Not yet, not yet.
Abhay, probably you can read all that, the people from where are they, and then.
Okay, sir. Okay, sir. These students are from Kurukshetra University, students are from IIT Kharagpur, and the students.
Now we can see your slide. Please make it in projection mode and go ahead.
Yes, sir. So these are the 61 participants attending all over the country. We are having students from Jammu and Kashmir. We are having students from Haryana. We are having students from Uttarakhand, students from Delhi, and we are having students from Bihar and the West Bengal, Telangana, Maharashtra, Andhra Pradesh, Tamil Nadu, Karnataka, and Kerala. So it's covering from north to south and east to west. And these are the 61 participants, mostly master students and 4 PhD students. And I hope this will be a good learning experience for you students. I request students, please utilize this opportunity. Lot of efforts has been made to organize this training program. This training program are organized like that. We are covering 60% theory and 40% practical. And we will try to address your queries. You please keep asking your doubts. And after this training program, we will also take an exam to know how much you have learned. And we will take the feedback from the participants. Please give your feedback so we can improve in the future about our training program. Thank you, sir.
Thank you. Thank you very much, Abhay.
I'm done, sir. PC, sir.
Yeah. So very good morning, Professor Gaur, the chief guest of the day, and Dr. V.M. Tiwari, Director, NGRI, all my colleagues, faculty, and students.
PC, sir, I'm done.
Yeah, that's fine. So I'm very glad that we are having Professor Gaur. It's always nice to have him with us.
PC, sir.
Yes, I'm speaking. Am I audible?
Yeah.
Yes.
Yeah. Okay. So I'm also glad that we have online Dr. O.P. Mishra, who is the director of NCS, and I can see some senior colleagues, Dr. R.K. Chadda, and many others. So hearty welcome to all of you. And as Abhay mentioned, this skill development program is an extremely important initiative of CSIR, and we are very glad that we had very good response. More than 70 applications we got, and I think 61 participants are there right now. So the basic aim from seismology point of view is that I think for the size of the country and for the kind of population and the geohazards that we face, it's very essential to train young people at the right time so that they are well equipped to face the demands, the challenges of facing the earthquake hazards in the country. And this activity has been going on, I think, each year. And I think that's an extremely important step that we have taken. And as the course coordinator, I would like to briefly mention that in this training program, which is about 12 days duration, so we have put in all the basic aspects of seismology as is required. And also we have blended it with some practical sessions. Although due to the pandemic, it's very unfortunate that we are not able to physically guide the participants, the students. But nevertheless, we are trying our best to do what we can online. So most of the afternoon sessions would be practicals, whether it is analysis of seismograms or it is instrumentation. Even we are trying to show how you are going to install seismographs in the field. So there's a very large, varied curriculum that we have built for the students. In fact, on the first day, we have 2 special lectures in the afternoon. One by Dr. O.P. Mishra, Director of NCS. He has very kindly agreed at a very short notice to share with us about the National Seismic Network and how earthquake monitoring is done in the country. And the second talk is by Dr. J.R. Kayal, and he has kindly agreed to speak about the great Himalayan earthquakes and the tectonics of the Indian plate. So subsequently, we shall have on each day a morning session, which will be the theoretical lessons, and in the afternoon, we'll have the practicals. And we are also glad that Dr. Lars Ottemøller from the University of Bergen, Norway, has kindly agreed to give a lecture on the seismic analysis software SISAN, which is very widely used in the country by most of the seismologists. In addition to all the basic aspects of seismology, which is the earthquake source, the earth structure, the seismic hazard, microzonation, and so on, we have also tried to include some of the very latest techniques that are in vogue. And we would like the students to be up to date, to be aware of where seismology stands in the world today. So we have dedicated the last 2 days to introducing various new concepts in seismology. We have also put a session on artificial intelligence and machine learning in seismology and how it can take the subject forward. So with these few words, I would like to once again welcome all of you and a hearty welcome to all the students, all the participants. I hope you will have a comfortable and very useful sessions for the next 12 days. And if any problem, you please contact me or Abhay. And we also have Vijay Raghavan, who is really playing a very crucial role in organizing this workshop. And of course, we have Dr. Prantik Mandal. He's coordinating this along with me. So please feel free to ask us any questions or any issues, any problems. So with these few words, I would like to hand over to Dr. Prantik Mandal. I request him to introduce the speaker of the day. Of course, Professor Gaur does not need any introduction, certainly not to this institute, but since there are a large number of participants, many of them are new to the field and very young people. So Dr. Mandal, could you kindly introduce the speaker of the day, Professor Gaur?
Yeah, thank you, Dr. Purnachandra Rao. It is a great honor to introduce Professor Gaur, particularly to young participants, because otherwise you all know Professor Gaur very well. Professor Vika God was born in 1936 in Varanasi, UP. He did his master's in geophysics from Banaras Hindu University, UP in 1955. Then he moved to London to complete his PhD in geophysics from the Imperial College London in 1959. In 1962, he came back to India and joined the University of Roorkee as a reader. Subsequently, he became professor in 1966. In 1983, he joined NGRA Hyderabad as the director of the institute. After 6 years of directorships, he became the secretary of DOD in 1989. In 1992, he joined CMAX Bangalore as a distinguished scientist. Since 1994, he is continuing to work at CMAX as an honorary emeritus scientist. Since 1994, he is also continuing to work at the Institute of Astrophysics Bangalore as a distinguished professor. He has got several accolades to his credit, but I will mention few of them. He has got about 150 research publications in the peer-reviewed journals to his credit. He has got several awards, including Shanti Saurabh Bhatnagar Prize in 1980, Clean Award of the American Geophysical Union in 2000, Saha Bharat Centenary Award of the Indian Science Congress in 2006. Professor God is a fellow of all three academies in India. He is also a fellow of the Academy of Sciences for the Developing World, TOS. In 2014, for his excellent performance or contribution to earth science, he has been conferred with the Lifetime Excellence Award in Earth System Science by the Ministry of Earth Sciences, Delhi. But I feel I would fall short of my duties if I do not mention a few more sentences about Professor God. He's an excellent teacher. He loves to interact with young researchers and students. So I wish a great interaction session with the participants. The participants kindly interact with Professor God. With these few remarks, I would request Professor God to kindly make his inaugural lecture. Yes, sir. Floor is yours, sir.
Thank you very much. Can you hear me?
Yes, sir. It's very clear.
Well, at the very outset, I must say I'm very pleased to participate in this program, which has been imaginatively designed to enlighten the minds of young people with the knowledge of how our living planet works. The only one in the entire solar system to be so structured, but in its beautiful and grand organization, like ourselves sometimes, it also suffers paroxysms, and those are sometimes hazardous to human beings. Fortunately, they also radiate the Earth with a kind of illumination called seismic waves, which allow us to image the structure of the Earth. And many illuminating approaches to this way of looking at how the Earth works have been revealed by the scientists over the last several decades, also in this country, particularly over the last 2 decades. And a very small number of seismologists in the country have contributed to this happening. India is also a very earthquake-prone country. Since the dawn of this century, we already have suffered a very large number of fatalities in the country because of earthquakes. And unfortunately, we have not been able to contribute much to the loss of life and property because in many cases they occurred in situations where it was very hard for us to foresee that that could happen. But today we have considerable knowledge at our command. The world of understanding about earthquakes and how to mitigate the hazards that they cause has been used by imaginative societies in making sure that even when earthquakes do occur, the damage to life and property is minimal. I have an ambition that our young people too would enable the country to come to that stage. But that would require translating the state of knowledge that we have into the state of practice and making sure that we can quantitatively estimate the hazards in terms of ground movements, particularly the accelerations, which are the main source of the forces that cause buildings to collapse. And it's the collapse of buildings which in turn cause the fatalities, not the earthquakes themselves. So I'm very pleased that this organization or this particular program has taken off. And from the numbers that I see, it is so gratifying to imagine that maybe in a short period of time, you would have a very large number of young people engaged in this fascinating and extremely sensible and urgent socially directed activity. So I hope you will enjoy this program and also that you will work diligently to grasp the essences of the theoretical basis of our knowledge and also the insightful ways in which this knowledge can be used to make sure that when the next great earthquake occurs in this country, it will pass. We will have our trauma for a while, but we'll be able to bounce back very soon because the damage caused would have been minimum. With these great expectations from you, the future of India, that I would like to inaugurate this particular program. Thank you very much.
Thank you, sir. Thank you. Thank you very much. I think we are all very eagerly waiting for your presentation. Maybe you could upload the PPT.
Yeah.
Yes, that's visible, sir.
This is a busy slide. But what I wish to say in this slide is something which will hopefully reverberate in the succeeding slides. And this is to show you very briefly how the planet Earth is organized. Something that it doesn't show are the movement of materials in this part of the planet, which is called its mantle. And those are the gigantic processes of mantle convection. Because they are driven by the flow of heat from the Earth's interior to its surface, that motion eventually causes the elastic rind of the Earth, this very thin layer called the lithosphere, to become strained. And when it is overstrained at places, then it fails, causing these earthquakes. And the earthquakes then travel around the world in terms of waves. And you know why waves are formed, why energy travels in the form of waves. Well, I leave it to your imagination. And maybe if there is some time at the end of this lecture, I would try to explain it as to why that happens. And that wave travels in a manner which is explained by this particular equation. And this equation is nothing more than what you have learned in your high school. And that is that the momentum is a quantity which is conserved unless it is disturbed by external agencies. So the rate of change of momentum must therefore be equal to the forces. And because we can relate the forces to strains suffered by the body of the material, and in turn to stresses, we can write this equation. This is the most profound equation in the theory of continuum mechanics, as it is called, and it hides everything that you will ever do while doing seismology in its various ways, when F is dynamic, when F is static, and of course, coupled with that process, which is ubiquitous in the universe called symmetry. That means that if I create an earthquake here and I detect the record at a point over here, the record would be exactly the same if the earthquake and the detector were actually exchanged in position. If I put the earthquake here, the detector there, the record will be exactly the same. And scientists have used that in a very creative way today to put seismometers imaginatively at places where earthquakes originate, so that you can even look at virtual records within the Earth of seismic disturbances which have been created as earthquakes on the surface. So this is the structure of the Earth, and this is the fascinating story of how this structure was formed, which you learned in some of the first lectures that I have seen, and how the energy, the strained energy which is stored for a while in this part of the earth is suddenly released, and then it travels in the form of waves. And those waves then travel in turn, they illuminate the entire earth, like X-rays can illuminate our bodies when you do CAT scanning. As you can see here, for example, this is layered earth, and we know exactly how to trace the path of a wave using nothing more than Fermat's principle or Snell's laws. And this is how it goes, because as the velocity increases with depth, it turns away from the normal, gets internally reflected, and back to the surface. Very fortunate for us, because if it were not so, then it will go inside the earth and the information would be lost. Coming back to the surface, it brings us all the information about this reconnoitering tour from which we can build the structure inside, just as some very insightful photographers today can build a very nice, sharp picture out of a very hazy one, or how scientists who get images from space can sharpen it. The same kind of principles, in fact, are at work here. And this is the unfortunate effect that an earthquake can produce. But if we can also produce the knowledge as to where on Earth and possibly within what time range, next 50 years, 100 years, 200 years, an earthquake of a certain intensity might happen, then that knowledge today can be coupled with another very important piece of expertise that exists, that we can create a structure which will withstand the accelerations produced by that event. Given that kind of an assurance, it then devolves the responsibility on us seismologists to be able to work out, not predict, because let me warn you that earthquakes, being a piece of critical physical process, are not predictable. But it is possible to estimate as to what is the probability that an earthquake will occur at a given place over the next given interval. And it is that kind of a knowledge which you have to sharpen. It is that kind of knowledge that you have to produce with diligence and with great, as much precision as possible. And wherever it is not possible to do it accurately, then we also specify what is the radius of uncertainty. What is that radius within which we can actually authenticate that knowledge? So this is what this slide aims to do. And what I wish to show next is that we happen to belong to a part of the globe which is between these 30 and 40 degrees north, and is one of nature's busiest workshop on earth. Enchanting lands, because the same processes that move different parts of the continents together, these two, for example, are coming together, as will be shown here. This is the picture of India about 40 million years ago. You see still there's a gap between the northern face of India and Eurasia. And since this time and the present, which shows the place of India today here, about 1,500 kilometers of this, its front face have been buried under Tibet. And in consequence, Tibet has been raised because of this crust upon crust, making a double crust, which you see over here. And this is the process whereby this takes place. And these materials at depth are viscous, they are soft, they move in response to this compression, because this movement causes compression. And as they move, they also strain the upper surface, which is brittle, but which cannot move, which cannot creep. But it can sustain strains, which will last for a while, steadily increase for a while, and eventually break. Because every material on the earth, like ourselves, have a breaking point beyond which stresses cannot be sustained. So this is the region where the Eurasian continent is colliding with Africa, Arabia, and South Asia. And this happens to be one of the most exotic places on earth, as you know, the whole of Central Asia, northern India, the Himalayas, and this belt contains some of the most dramatic geomorphic features. If you happen to look at the globe here, you see where most dramatic features are. They are here. And great civilizations have erupted here. We have had tragic encounters as well. Himalaya, which crowns the earth, is a piece of the southern Eurasian collision zone. And the region witnessed the highest earthquake fatalities since 2000. But this is an example of how societies have used this knowledge to incorporate in the practice of design and construction of buildings, that an earthquake of magnitude close to very 9, which occurred in 2011 over here, and it shifted the island of Honshu east by about 2.4 meters, and the Earth's axis by 10 centimeters, and buildings in Tokyo swayed by tens of centimeters, as you can see here. And all this because that knowledge gained from these records, which seismograms make, very imaginatively used to design and construct the buildings that will withstand the fury that is unleashed by this event. But here in India, we have not been able to do that. And I believe, and it is my fervent expectation, that after I pass away and the young seismologists in this country, looking from the numbers that you have today, grow by leaps and bounds, can greatly reduce this contrast. And we too can boast of a day in not too distant future where something like this will happen, where a big Himalayan earthquake might shake the earth violently, but will not hurt the life and property of the people in that region. And it is my fervent appeal to you all that instead of wasting our time as to asking as to where magnitude 7 will occur there, or 8 or 9 will occur there, let us put energy into the arguments scientifically made, rationally constructed, and quantitatively shown that such and such could be or will be the future scenario with so much probability. And that is where we should put our energy. So the challenge, young people today, is to move away from my generation's imitative science. It's a harsh verdict, but unfortunately it is true. We have generated a lot of knowledge about the structure of the Indian continent and the lithosphere, but in all this we have only used the analytical approaches which have been developed elsewhere. The lecture that I give you must be viewed with the same skepticism. Do not be led by everything that I say. Scrutinize it, not just listen to it. And move away from my generation's imitative practice to your own generation's creative science. You do that by combining rigorous understanding and audacious imagination. It is all in your head. It is given to you by nature. And I wish that you utilize it. Make a beginning today. So this is an evocative context for imagining as to what kind of puzzles there are that one should devote one's life to solving. Most parts of India are prone to earthquake hazard, as you can see from here. And this is no longer a matter of debate. We don't have to debate as, of course, we can see that some parts are more intensely stressed than others, but you can see that there is no place where earthquake occurrences are completely absent from. And this is both a matter of celebration as well as caution. Celebration because it's evidence of a living body, living planet, living lithosphere, which is involved in one of the most dramatic encounters on Earth, moving at the rate of about this Indian continent at the rate of about 5 centimeters towards Eurasia. So if you held a part of a string here and another at Lake Baikal, somewhere over here, you will find that that is strained by about 5 centimeters a year, 2 of which is used up here in the Himalaya, because as India dives under the belly of Himalaya. So you can see that on all sides we are stressed. It's a living lithosphere. It creates dramatic landscapes. Hopefully, it will also give energy to our scientists to create insightful knowledge, knowledge that can live for centuries, rather than techniques which are changed or which evolve almost every decade. So this is the knowledge that has been created, in which many Indian scientists have made a contribution, creating that knowledge, but not conceptually. And that is my lament. And that is where I hope that some of you will make a contribution, where you develop not only information, but also insightful knowledge. It came to light in the late 1990s that if you take a point here and somewhere at the very northern front of the Himalaya, you find that the average annual movement between these 2 points is about 18 millimeter, and this shrinks the continents. But as we keep this point constant somewhere here in the peninsula, let us say Hyderabad or Bangalore or somewhere else, Nagpur, and as we move from this northernmost point to the foothills, we find that this 18 millimeter shrinks to about 2 millimeter. And we have these values now fairly strained after 20 years of work by a large number of groups, that there's very little doubt that this indeed happens. That means that 16 millimeter gets almost used up here, 16 millimeters of shrinkage. At least about 2 or so does occur between the tip of the peninsula and the foothill of the Himalaya. And there's a cartoon here to show that. Here's the foothill. And this cartoon explains as to how this happens. As the Indian continent is moving at the rate of about 5 centimeters with respect to somewhere here. And this part obviously is riding over here, because the depth here is about 15 kilometers below the surface, where rocks are molten and materials can slide. And then as the material slides, it moves upwards. As it moves upwards, it encounters a region where the material is cold and therefore brittle, and therefore it cannot slide, but it can strain itself up to a limit, which when exceeded will eventually break the whole thing, and this entire green part will lurch over the Indian plates by as much shrinkage as has happened here. And then that will be a great earthquake. Meanwhile, of course, as the strains build, there will be squeaks over here, smaller, moderate earthquakes, alerting us to the fact that the strains are building, and they will sometime in the not too distant future approach failure. So be careful and make quantitative assessments from the information that these earthquakes produce as to what might happen in the future, and prepare for it, prepare our cities for it, prepare our municipal infrastructure, and make safe that our telecommunication, our vital supplies, large places of worship or instruction are all safeguarded against a long-term occurrence of damaging earthquakes. So how do these strains evolve? And here's a cartoon to show it, and I'll go over it quickly. Here is Tibet, here's the Indian plate, and this is the imaginary plane we have drawn here, which marks the upper surface of the plate going down, and this part which is coming up. And I'll show you, mark it, how as this process goes on, how these strains accumulate here, till the breaking strength of the material is exceeded and an earthquake happens. On this plane, a rupture takes place, moving this entire region forward over the Himalaya. So this is how it goes. And you see how this stressor, how this is even being lifted over here elastically. And now, and you see how it's more lifted, and then suddenly, and then this thing goes down. We now have quantitative knowledge of what happened to Kathmandu when the 2015 earthquake took place, like this. What happened over here? This, nothing was happening, nothing was moving, and suddenly when this part moved by about 3 or 4 meters, then this is what happened. There was a co-seismic slip deficit between Kathmandu and MFT, unfortunately, because this part has not moved. And that's a cause that concerns us, but not frighten us, because we can turn that concern into a credible knowledge of what will happen to the plains of Bihar when this breaks, because all this strain has now been piled up over here and is bound to be released in some future earthquake. But this is how the dynamics of the landform, Kathmandu, as you see over here, it shifts Kathmandu 1 meter south and up, but there is no surface rupture over here. The surface rupture just stops short of here. And what had risen here has come down here. So this is what we have learned from the Kathmandu earthquake. You can imagine that this is the surface of the Indian plate, top surface as it goes down. And you can see with what precision all this has been mapped, made possible from the detected waves or seismograms that were recorded on the surface as this earthquake moved on. That is the kind of knowledge we need to produce. And mark here that this surface is not smooth. It has flats and ramps. As you see here, there's a sharp ramp here. Then there is a gentle dip, again sharp ramp and gentle dip. Why should this happen? Is a part of continuum mechanics and something that can be modeled, all implicit in the same equation that I showed you at the very surface. If you took away if you made the surface, the force is static, it will yield all the solutions that it needed to produce this kind of a map. And what this map tells us that this angle is very critical in certain ways over here. And I'll try to explain to you as why. And therefore, it is extremely important that we should be able to image the geometry of this surface with as much precision as possible, so that we might be able to say that, okay, the earthquake, when it occurs here, will be something like what Kathmandu earthquake did, come halfway, and then the rest of it in another installment. All that can be done if we know this surface. And the implication of this surface is over here. This is, if the surface is like this, and if the temperature, if the level of the earth, beneath the earth, above which the temperature is less than 350 degrees, it is elastic. If it is more than 450, it is viscous. And in between, we have a material which is viscoelastic. So what happens is that if this inclination is less, like 10 degrees, then this zone between the viscous and the elastic, between this part and that part, is much wider than what it would be if it were 35 degrees. For example, over here, it is only this. So the cartoon that I showed you of the interrheological zone between the elastic and the plastic behavior of displacement depends on the angle of this ramp. And it is extremely important to be able to map that ramp. And you can test, you can examine and study this, the remainder of this slide, because it's as self-explanatory as possible. And you can even convert, because we roughly know what is the breaking strength of material. If you know the rate at which the material is being stressed, the rate at which the strain is being produced, then you can calculate what is the time it will take to reach up to the breaking strength. And somewhere around there would be the time, which may have an interval, an uncertainty of 50 years. That would be the time when that particular earthquake will take place. So that zone also tells us as to how this part, which is locked by friction, because it is elastic, it can only fail when there's enough strain produced at its back, and this part which is viscous, how these are separated. Can we map this zone using, for example, the GPS, and certain scientists, including those in your own institution at the NGRI, have produced this map or helped produce this map, which shows the strength of locking, known as the coefficient of locking, 1 when it is absolutely locked and welded, and 0 when it is slipping, and in between, of course. This particular picture is from this particular paper over here, cited here. And I cite this paper rather than any other because in the preparation of this, they have used a very large number of independent indicators rather than any one particular evidence like GPS. They have used GPS, they have used topography, they have used various other features to determine this. And therefore this has, but I believe this has higher reliability. So what is the knowledge that we need to produce? We need to produce that, since we know that whatever displacement takes here and produces the compression in this zone, and this zone is largely locked so that it refuses to move. This one is moving and it compresses this zone, as you see over here. The small earthquakes, moderate earthquakes begin appearing as this zone is more and more compressed. And finally, when it can't bear, then this gets uncompressed like a spring which fails. And this part, as it moves forward, it does that. So this is what we have to calculate. We have to calculate what is the available strain budget at this time, and where, how wide, and I've shown you the angle will tell you whether it is this wide or that wide or this wide, and how well locked are those locked zones that I showed in the previous slide. So what is the available strain budget? How do we calculate that? What we do is that we can calculate, we can catalog all the earthquakes that we know have taken place, the smallest one, calculate all the strains that they have released in different parts of the Himalaya. And you can see here, all this tells you as to, so these are the earthquakes, cumulative earthquakes in those particular segments which have released these strains. That is the strain which the pushing of Tibet over the Indian continents have produced, and therefore you can calculate what is the available budget. Here's an example of a locking line. You see there are very few earthquakes here, but there are a large number of earthquakes here. This is a picture by this paper, and it's a part of Uttarakhand, Himalaya. So you can see where this particular line goes. And over here is one of the very tall dams of the country, but hopefully it has been constructed with enough strength to withstand the forces that this earthquake might produce. But so locking line can be found out because south of the locking line, the incidence of earthquakes will be minimal. So how do you find out the locked zones in the Himalayas? This is the one that I showed in the last slide. There's an intriguing cluster over here, and that shows the earthquakes that have happened, and different magnitude earthquakes. And all these have happened like Nepal earthquakes. They have not broken the entire boundary right up to the surface. They have only broken half of the locked zone. And why? Maybe because there's a ramp here. Maybe because between here and there, the slope is rather large, and because the slope is large, they were not able, it was not able to move this material further south, but it certainly will when the strains increase over here. In how many different ways which earthquake may occur, and what are the probabilities? So there are potential leads for this, and I'll leave this for you to study because it will otherwise take me a long time to explain. This is the way the Nepal earthquake broke. Up to here, over here, this is the 2015, it should be 7.8. This was a 1934 earthquake. This is the only earthquake whose surface rupture we actually see in the foothills. But all these are also going to complete the history. And it seems that this is the kind of a pattern as we see in the Himalaya here. All of them have ruptured halfway, all these earthquakes. And they're all preparing to drive and rupture the locked surface further south when the strains become high enough. If we only knew as to what were the slope of the ramp by designing imaging technologies which are very sharp, then we would be able to make an estimate, very reasonably good estimate of what could be the earthquakes at the remaining strains here would drive in the future. These are the various ways, for example, in the Kashmir Valley, that someone, not me, imagined the earthquakes could actually happen by the slippage across here, by here, all these possible ways. And given each way, one can calculate what is the ground shaking that will be caused. So that is one way of doing it, that one finds out what are the possible faults along which ruptures could take place in the region. And then these 3 steps, identify all the faults within a few hundred kilometers which are capable of producing significant ground acceleration at any site, X, Y, Z, estimate their dimensions, compute ground acceleration, and fuse all these values to get an estimate which has the minimum variance, which has the highest reliability. But whilst doing all this, whilst calculating this ground motion, make sure that the slip, you understand, or one understands that the slip is not going to be uniform. This is the slip, for example, in one of the large earthquakes that took place, and you can see that the slip at the ends is 0, more or less 0. In the middle, it is almost 5 meters, but it tapers off at both ends, as it should. And one needs to know this history also, and this history can also be imagined. It can be imagined as this scenario will show how the earthquake is moving along this plane. It doesn't all happen in one go. It happens sequentially. And once one has done that, and actually one has then calculated this, so you have to put that process here, calculate all that, all these ground accelerations are calculated here at different places, you calculate that, and then because this procedure will allow you to do that only considering that the entire material between here and the earthquake is made up of solid rock. But should there happen to be a sedimentary load somewhere under your site, under a particular site like this, then one has to take care of that also. And one does that after doing that by feeding whatever the rock you expect by feeding onto this sedimentological section and then finally computing what the ground motion is. So all that can be done. To the design world, earthquake hazard is quantitatively expressed as the probability that the ground motion at a given point over a given interval will not exceed a certain value. So this is the way scientists today express hazard. At this particular site, for example, what is the hazard? The hazard is 4 to 8% of acceleration could happen here, 4 to 8% of G. So if G is 1000 cc, 1000 centimeter per second, this will be about 4 to 8 centimeter, 40 to 80 centimeter per second acceleration at any point over a given number of, that is given over here, is perhaps 50 years over the next 50 years in this region. So that is all that you need to find out. But once you have found that out, that becomes a magic figure, that becomes a solid figure for the design engineer, because he can then construct a building here, a dam here, a nuclear power station here, depending on the expected lifetime of that particular structure, and ask the question, what is the probability that an earthquake of a certain magnitude will not occur over the next 50 years for a building, 500 years for a dam, 10,000 years for a nuclear establishment. And once one has got that, then the next thing is that, okay, our old cities have not been designed with all this knowledge. The old cities still have structures which are susceptible to damage. So can we find out as to what is the risk involved? If they are very well built, then the risk is zero, even though the hazard is high. This is the vulnerability. The vulnerability of buildings, of structures, can also be computed on a 0 to 10 or 0 to 1 scale, and you can then convolve it with the hazard to get the risk. So if the hazard is high but the vulnerability is 0, the risk is 0. If the hazard is low but the vulnerability is high, so that is small, even a small earthquake produces very large fatalities, the risk is very high. So this is the other part of the game where we need to involve social scientists, structural engineers who can examine the building typologies and assign vulnerability. And then knowing as to what is this value at that particular site, retrofit that particular building, that particular infrastructure facility, so that it will withstand that kind of hazard. So what's the state of knowledge towards making a hazard resilient society? Ability to construct land use maps that maximize resource generation, we can do all that if we know the hazard map of the region. Structural engineers can design, construct, and retrofit buildings which will withstand that. And what we need is the ability to construct suites of hazard maps for guiding these first two. They are dependent on these kind of maps that can produce. And that shows the acceleration that has a 5% exceedance chance over the next 50 years at this particular site, and the accelerations are given away there. So that's the challenge. This is the hazard map of the United States, for example. It will be nice if using all this knowledge that is available here, and of course, the knowledge of faults can be progressively improved as geologists improve their methods and methods of detection and analysis, and we can end up by having a map like that, which we keep on updating as all this knowledge progresses. So it's not a one-time job, but at least we must get to the zero-time job of doing that. I have been impressing upon this on various government and instructional academic institutions to produce a map, to train our scientists to produce a map like that. It will be nice if such a map would be available in the near future. We need to move on to first principle science about quantitative hazard in Indian shield. And there is enough knowledge to be able to do that. Here is a finite element stress model of the Indian continent subject to boundary stresses. And the paper it came just about a few weeks ago. And you can see that stress has been modeled. These are the values of stresses in terms of Newton meters. And we can also calculate stresses using the methodologies or approaches that I have shown previously, the previous slide. And of course, one can improve those, both methodologies and ways of doing it through creating more insightful knowledge, and use both of these to improve our knowledge of stresses in the Indian continent. And knowing that knowledge of stresses, because remember I said that even between the foothills and the tip of India, there is a shrinkage of about at least 2 millimeters, if not more. Even though it's about 2,000 kilometers, that 2 millimeters over 2,000 kilometers produces a strain which you can calculate. 2,000 kilometers will be 2 million millimeters, and 2 millimeters, so it is 10 to the minus 6 per year, and it can reach 10 to the minus 4 in a few centuries, sometime in millennia. So over the Indian Peninsula, where we have few leads as to where earthquakes occur, unlike the Himalayas, we can still use this knowledge to put some upper limit. And here's an idea for your criticism. You criticize it, debate it, and you will see how we can produce a hazard map even for the Indian Peninsula using those particular principles. So this is the kind of activity that we should aim at for the future. That is the challenge, something I started by when I started this lecture, and something I'd like to end with, appealing to your imagination, your drive, your initiative, your inspirations to accomplish, so that the task that you are charged with by the nation, if you choose this profession, the nation will charge you with a certain responsibility, which is responsibility in return for which it supports you. But this is what you have to do for the nation. Make sure that next time when a big earthquake takes place, we can go proudly and show that we have also been able to safeguard life and property and do something what the Japanese were able to do. Thank you very much indeed.
Thank you very much, sir, for a very exciting as well as challenging talk that you have delivered. And I'm sure all the young students must be pretty excited after listening to you. You have so nicely explained how we should be looking at the locked zones in the fascinating and yet seismically active Himalaya-Tibetan region, and how to understand the strain budgets and work towards probabilistic estimation, and in the process also understand the vulnerability and the risk aspects. In any case, you have rightly pointed out that we need to be prepared for a great one round the corner anytime from now, and you showed us how we need to build a resilient society to mitigate hazard through the various earthquake engineering techniques. And I really appreciate your call to move towards a more original and creative science. And I hope your ideas are well imbibed into the young minds, which would ensure a better future for seismology in India. So thank you very much, sir. Once again, it was a great pleasure listening to you. And I'm sure this sets the ball rolling for the next 12 days of course that we are going to have in the few coming days. Now I would like to request Dr. Vijay Raghavan to propose a formal vote of thanks.
Yes, sir. Thank you, Dr. Purnachandra Rao, sir. It's my pleasant duty and privilege to propose a formal vote of thanks. First and foremost, I would like to express our sincere gratitude and appreciation to Professor Vika God, Honorary Scientist, CSIR 4th Paradigm Institute, Bangalore, and former Director, CSIR-NGRI, for accepting our invitation at a short notice to be the chief guest and inspiring young minds with his great wisdom. Sir, we have really enjoyed your excellent presentation, and I am sure that all the participants must have greatly benefited. Sir, I hope we will continue to have your association that will benefit a lot of young research students in future. We are very grateful to Dr. V.M. Tiwari, Director CSIR-NGRI, for his great enthusiasm and guidance for organizing this training program. His total support and that from Dr. M. Ravikumar, Head of Seismology, has enabled our training course coordinators, Dr. N. Purnachandra Rao, Dr. Pratik Mandal, to organize a very comprehensive lecture series. I thank Dr. Abhay Bansal, CSIR Skill Development Coordinator, for providing all the necessary support, both at CSIR level and at our institute level, for organizing this course. We are thankful to Dr. Kalyan Neti, Head of IT Group, for all the technical support and conducting this course online. I am very grateful to all the faculty members for accepting our request and sparing their valuable time to deliver their respective lectures and interacting with the students. We would like to particularly thank Professor J.R. Kayal, DDG retired, GSI, and Dr. O.P. Mishra, Director NCS, who have kindly agreed to deliver the invited lectures. And also we thank Professor Lars Watermiller from University of Bergen, Norway, has kindly agreed to deliver the lecture on SISAM, the seismological application software. We also thank Dr. O.P. Mishra, Director NCS, and our senior colleague, Dr. R.K. Chadda, who have joined this inaugural program online. I am thankful to all the participants for the enthusiastic response to our call and for attending the training program with great interest. I hope they will enjoy this training program and it would be a memorable one. Thanks to all the volunteers who are helping us to organize this course during such a difficult pandemic time. Finally, I thank one and all. Thank you very much.
Thank you very much, Raghavan. So with this, we come to the end of the inaugural session. I once again would like to thank personally Professor Gaur for making this so very exciting session. Sir, Professor Gaur, you are there, sir? All right. So we come to the end of the inaugural session with this. We'll have a break of about 5 minutes, and the first session will start at 11:30. So may I request everyone to sign out except the participants and the organizing members. So we'll meet again at 11:30. You can have a short break of 5 minutes. Thank you. Thank you very much.